speaker of the morning. It's my great pleasure to introduce Nate Lewis. Nate is a very distinguished professor at Caltech. He's Georgia Garnet's professor of chemistry. Nate has been working for many years on many different things. One thing he worked on years ago was on olfactory sensation, amongst others. But he's most recently received a large grant from the Department of Energy to establish a hub to try to generate hydrogen and produce fuels without bugs. So, Nate, welcome.
Thank you. What I'm going to do is shift gears a little bit in that I'm a practicing scientist, and I'll tell you about our little effort scientifically to try to move ahead toward a technology that could be one of many possible options. It's important because when you look at the portfolio of options that we now have on the table for energy security and environmental security, everybody can tell you about everybody else's main problem. And that's what we'll do. Well, nuclear power plants, we're never going to build all the ones we need, and if we did, then we'd run out of fuel, and natural gas has problems because of blah, 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 blah. And so everybody can tell you everybody else's problem, and that's what we really struggle with. We really struggle with the fact that we have gaps. The knock on renewables is pretty simple. Intermittency. Unless you have a way to compensate intermittency and massive electrical power storage, of which there is no cost-effective technology now to do it, you can build all the PV you want. The sun goes out at night, dead in the water. So everybody can tell you everybody else's gaps. On the other hand, we need to be working on ways to bridge those gaps so that if we have a plan to get from here to there, we don't run into the Grand Canyon and then decide we have no path to cross it and we're stuck in our tracks. One of those gap-filling options is, in fact, to take the biggest energy source known to mankind, which is the sun, to calibrate you. The more energy from the sun hits the Earth in 1 hour than all the energy consumed on our planet in an entire year, and to find a way to cost-effectively not make electricity out of that, but also to store that energy and distribute it wherever people want it, whenever they can use it. So that's what our job is in a process that we call artificial photosynthesis. I'll tell you about what that is in more detail, but our little slogan is we want to make fuel from sunlight with no bugs and no wires. I've already told you what the shortcomings are. We can take this massive energy source. By the way, I believe the answer is clearly to all our energy problems is nuclear fusion. No question about it. Nuclear fusion is the answer. We've already seen it's probably a pretty good idea not to live too close to a nuclear power plant. And you know, 93 million miles away sounds just about right. You can efficiently convert that into electricity, but no matter how cheaply you do that, no matter how many routes you do that, the sun has this nasty little habit. It locally goes out every single night. And unless you find a way to massively store electricity cost-effectively, which I would argue the only way conceivable to do that from a physics basis is in the most energy-dense form of storage we now know, other than the nucleus, that's chemical bonds. The next alternative might be the way we do it now, which is pumped water, uphill, pumped hydro. But let's look at physics. If you want to store the energy in 1 gallon of gasoline, you have to pump 55,000 gallons of water up the height of Hoover Dam. That's the energy density problem of the chemical bond energy versus the energy in MGH in pumping a massive cheap water uphill. Batteries, the best battery is 200 watt hours per kilogram. The energy density in gasoline is 13,000 watt hours in kilogram. You don't have to know anything more to know why range in an electric vehicle is going to be a challenge. Or volume storage for even powering the home overnight is going to be a challenge unless you find a way to do it in energy-dense forms. To give you another calibration, if you took the stored energy in all batteries built in human history, collectively, they would, if you unplugged our electric grid globally, power the Earth for less than 10 minutes. Okay? So this is the storage challenge that is accompanying the intermittency that we have to live with the sun and with the wind. Plants figured it out. They store energy in chemical bonds. They get an A for the idea, they get a D- for implementation. Because not only do they not make a fuel that humans can use, that lignocellulosic stuff, or algae or oils we have to process, but there's a fundamental problem. Photosynthesis saturates its productivity at a tenth the light intensity of sunlight. All photosynthesis does this because there's a rate-limiting step to move that quinone between photosystem 1 and photosystem 2, and that's a molecular diffusion time scale. Plants were not optimized for energy conversion. In fact, the fastest growing plant, if you take all the energy produced by all the biomass, and you divide that into the total sunlight that hits that same square acre over a year, the fastest growing, best test plant is less than 1% of the total sunlight is stored in all the chemical bond energy on a free energy basis in all of it. And then we have to pay a penalty to go get it, and to go farm it, and to go cultivate it, and then go extract the stuff we want. So by the time you are done, you're lucky if you have a tenth of a percent. And only because the sun is such an enormous resource would we consider something which is 99.9% inefficient as the machinery that we might use to make some fuel for us. Now, by the way, I think biofuels are important and should be pursued because even at low efficiency, which is ultimately why we have food for fuel land trade-offs, unless we develop another approach, we simply cannot get to a low carbon emission target. And despite the fact that we have all these portfolios and all these wedges, I made an uncategorical statement. The reason I made that is because right now, out of transportation, 40% of global transportation fuel demand is in heavy-duty ships, aircraft, and heavy-duty vehicles. And there is no such thing as a plug-in hybrid airplane. So we have to find high-energy-dense liquid fuels in order to decarbonize that significant segment of our energy demand or shut down global commerce. It's pretty simple. So the missing gap is how do you take and decarbonize fuel, which also, by the way, solves the storage problem, because if you had a decarbonized fuel source, you could then burn that like natural gas in peaker turbines in a carbon neutral way also, without which you can't solve the massive electrical storage problem. So if you think about making a full energy system, one of those key chasms is how do you make a decarbonized, abundant, cheap fuel from a big energy source, and the biggest one around is the sun. Now, that's what we do. This sounds like magic, but it's not magic, it works. Now, this is a mineral, it's called strontium titanate, and this mineral, and I hope this movie transferred, but if not, I will just describe it. It looks like it did. When you shine sunlight on it, maybe the media not found, but you can see the bubbles in this snapshot, will produce hydrogen and oxygen directly from water with no other inputs, no living systems, no wires, and this will last for years. And already, the free energy content of the hydrogen gas that is produced is 5 times greater than that of the fastest growing plant in terms of a total sunlight energy that hits the system divided into the total free energy of the fuel produced. So we already know as humans that it's possible to do better than the fastest growing natural system without the fundamental engineering constraints of having to move around electrons in molecules that photosynthesis actually faces. So why don't we have these things on the roof tomorrow? Well, because there are three things we want. You want them to be efficient, you want them to last a long time, and you want them to be cheap. And right now, we can give you, after 30 years of work in individual labs, any two out of those three. If you want it to be efficient and last a long time, it isn't cheap. If you want it to last and be cheap, like this, it isn't efficient by a big picture scheme. If you want it to be efficient and cheap, it doesn't last. So the job is to try to find a way to get all three at once, because that's the only batting average that technology will accept. What's the blueprint? We think a blueprint is photosynthesis, but just like birds give us a blueprint to fly with feathers, we don't build aircraft like 747s with feathers, we build them with advanced designs. That the blueprint is to have two different photosystems. Because unlike making a photovoltaic cell, if you're trying to make fuel, you have a first law of thermodynamics that is a constraint. You need to develop enough voltage to make and break chemical bonds, or you get nothing out. Unlike in a photovoltaic cell, when you can trade voltage for current and string them up arbitrarily to make any voltage you want by just hooking these things up in series or in parallel. So we have to make 1.23 volts to split water, or we don't get anything. If you want one material to give you that voltage, then by the time you include the other constraints, it ends up having to have such a high band gap that it doesn't absorb much visible sunlight. And this is this robustness, cheap and efficient trade. So it's pretty clear that nature did figure a way around that. It uses two such photosystems, and by getting half the voltage it needs out of each, it can hook them together electrically in series, just like two D cells together to give you 3 volts instead of 1.5. In this case, it takes two chlorophyll pigments, each of which are 1.7 eV, green looking, red light absorbers at 670 nanometers, each of which produces, when all is said and done, about 700 millivolts of chemical driving force. And it strings them together electrically in series to make the total 1.4 volts needed to split water to oxygen, and in photosynthesis to reduce and fix carbon dioxide, with the intermediate step of really reducing protons to hydrogen and then fixing them in the chemical bonds of hydrocarbons. The next design principle is that unlike our one material that had to be both oxidatively and reductively stable in the same place at the same time, we don't have that constraint. The material that reduces protons to hydrogen, or that makes Rubisco fix CO2, is not oxidatively stable, but it never sees an oxidative environment. The manganese site of the oxygen-evolving complex that Chuck Desmukes here knows so much about and has helped us learn so much about how to model with chemical systems that makes all oxygen is not reductively stable, but it never sees a reducing environment. Because these systems are strung together across a membrane that is needed for another purpose. Not only do you need the membrane to eliminate the stability problems of both reductive and oxidative at the same place at the same time, but it's a good idea not to make this fuel in the same place at the same time unless you want hydrogen and oxygen above the lower explosive limit in a system the size of a farm, which nobody would make in practice. And on top of that, this membrane has another constraint. It has to pass protons, because you have to neutralize the pH gradient that would otherwise build up and the system would stop. And without these key features, two photosystems, a membrane to separate the products, enable differential stability, and pass protons, you don't have the key ingredients in the design blueprint to build a whole system. So it's those ingredients that we need to copy somehow and make human embodiments of. That led us a few years ago to this design, which was nothing more at the time than a PowerPoint view graph with a catchy slogan that said, "Powering the planet," that we thought big. It was big enough to get a group of scientists, both from MIT and Caltech, National Science Foundation Center for Chemical Innovation grant. And in our design, what we have is we have an assembly of pigments, except they're made out of a little on nanoscale that I'll tell you why, pieces of semiconductors that are much more stable and more efficient than chlorophyll, converting and capturing sunlight. In addition, these are high aspect ratio structures for reasons I'll technically tell you about later on in the next slide. And they're wired together electrically in series, each one of which can only be reductively or oxidatively stable, separated across a membrane that passes protons and separates gases. But there are no external bugs, no external wires, and an embodiment of this, if we succeed, would end up being something like bubble wrap or carpet that you would roll out anywhere, and you'd plumb in water and CO2 from the air, and out would drip or wick either gaseous or liquid fuel. So this is what I would call a fundamentally disruptive technology approach, in that it is nothing like anything we currently deploy. It is not purely an evolution of existing systems, but it would fill this chasm-crossing gap of how do you make storable, energy-dense fuel from a renewable resource. So that's the idea 4 or 5 years ago. Well, the concept of using these rods was, A, we needed to bridge our membrane, but still leave space to pass protons. Because if we didn't do that, we knew the system would shut down. And so you see now demonstrations of breakthroughs of the century, people claim, where they take a photovoltaic cell and then make bubbles, but those bubbles don't last for very long because you build up a pH gradient that is blocked by that dense inorganic solid. So those are really more publicity stunts than advances in science. What we have to do is we have to put this in a membrane that crosses the protons and find a really cheap way to make these light absorbers work well. And the idea that we had was that the reason that most photovoltaic cells cost so much money lies in the physics of light absorption. You have to have a certain thickness of something like silicon to absorb sunlight. It's 200 microns for a piece of silicon. You can't do anything about that. That in turn, however, dictates why that piece of silicon that's useful must be the purest thing that any human will ever touch. It's pure to a part per billion. And the reason is that the light's absorbed unless it's so pure that the excited states can make it all the way back that same 200 microns to then hit the wire and make electricity. Impure material will just capture those electrons along their path and make heat. And you might as well spit asphalt on the surface instead of making that semi-pure silicon. And so that dictates the cost. It's the fact that carriers have to travel back the same way that they came, and therefore have to have a so-called diffusion length that's as long or longer than the light absorption depth. And that requires expensive material processing to eliminate the very last traces of impurities. So in this design, we said we don't want to struggle with that fundamental constraint. We want to change the playing field, so we'll change the rules. And the idea is we'll have very long structures to still absorb the light. But if carriers in cheap material can't go very far, so be it. They can't go very far. We'll just make them go sideways a short distance and live with that constraint, provided we can make a radial geometry junction that then we can take cheap materials that no one in their right mind would ever use here, because if carriers could only move 1 micron, the other 199 would be dead. Here, all 200 can be live because they only can move 1 micron sideways, and we can collect them all. Well, when you then draw this design, you see nature drew this design and implemented it successfully in many different environments. That's what aspen trees do. They have a long axis to absorb the light and a short axis to move the heavy, slow-moving nutrients like water and things sideways. That's what root systems do. That's how they're organized to feed nutrients. That's what leaves do. That's what stomata do. That's what retinal rods do. That's why they're retinal rods, because they're long to absorb a photon effectively, but they're short to move the heavy, slow-moving calcium second messenger sideways over a short distance so your eye can effectively know you saw a flash of light and a photon. And there are many examples of this in nature, so it sounds like something that humans should try to mimic. So now we just have to build one of these things to see if it's right. Now we did modeling. I'm going to skip lots of work over the last 4 years since this was PowerPoint and tell you some of the nice pictures and results that we have that will lead into this next phase that I'll tell you in the end about our DOE hub. One of the materials that we wanted to grow these rods out of is silicon, because it is A, useful for making hydrogen from water because it is reductively stable. You can't reduce silicon anymore chemically, but not oxidatively stable. It makes silicon dioxide, which is sand, which is an insulator. So it's not a good idea to keep it oxidized, but if we can keep it reduced and use it only for reduction and separate it from the oxidation, we can circumvent one of the fundamental challenges there. But single crystals of silicon are too expensive for us and are too dense to be used, so we want to grow these silicon high aspect ratio structures and embed them in this membrane to see if it will come alive. We tried to electroplate materials. We showed this would work in concept. We developed the modeling and showed that this high aspect ratio structure should work on a piece of paper. It worked in PowerPoint. It worked from the device physics viewpoint. We implemented it with cadmium selenide telluride as demonstration systems. And we've recently succeeded in bringing forward a method of using silicon to do this. The way we do this is with the so-called vapor liquid solid growth approach, where you take a silicon vapor precursor like silicon tetrachloride, and over a growth catalyst, there are 3 suitable growth catalysts, according to the phase diagrams, gold, copper, and nickel, that will crack that silicon and make a molten silicon gold alloy. And as you feed it more silicon precursor, in our case at atmospheric pressure, so in something like a toaster oven, literally, then you dissolve more and more silicon until it reaches its solubility limit. And then it has only one place to precipitate, and that's at the phase boundary between that alloy and a crystalline silicon substrate. And because that's the only place it can precipitate, it will be like growing seeds of corn into stalks of corn, and the molten catalytic drop will ride along the top of that growing crystallite of silicon until you stop feeding it precursor. Now, this is an example of a 1964 first paper of this, and that scale bar is 0.5 millimeter, showing the single crystal of silicon grown by this vapor liquid solid growth method. Now, this is the poster child of the silicon nanoscience community. You grow such VLS rods, you get a whole bunch of felt because the wires grow everywhere. You ultrasonically remove one. There are over 1,000 papers to do this. You publish it on the cover of Science or Nature and declare victory. On the other hand, none of them are good enough for us for 2 reasons. One, it turns out nano is bad here, micro is good for technical reasons that I'm happy to explain later. But 2, we have to orient all our wires directly toward the sun, and there was no established method to do that. They grew felt everywhere, and you can remove one of those wires, but that's not what we needed. So we developed a process by which this works. Again, I'm condensing, in this case, 6 months of work into one slide. We tracked down why people, including us, kept getting that felt-like morphology. Even when we patterned deliberately with photolithography gold dots onto a silicon substrate, we found the reason we grew felt was we don't maintain the integrity of that pattern under growth conditions. Even in the absence of chlorosilane, just under reducing conditions, of course, SEM shows that after 10 minutes, under growth conditions, all those metals don't stay put. They move around and they agglomerate and anneal. And so even if you take pains to start with this template, this is what you get 5 minutes later, and it's no surprise that stuff grows everywhere, all over the place. And the way we fix that is if you don't like where your seeds in the farm are growing roots, you should put each one in its own pot. That's what we do. There's a silicon oxide layer. That silicon dioxide layer, we etch holes in it. We can find the metal seeds in those sand pots, and it has nowhere to go, and so the pattern stays robust. In addition, we get smart about the depth of that pot, because we know the surface tension of the molten drop of that metal eutectic on the growing seed, and we make sure there's just enough metal for the diameter that we want to grow that it fully covers the diameter of the growing drop. If there's too little, it's going to pool up into little spots and grow filament filt. If there's too much, it's going to drip down the sides like wax over the side of a candle, and we're going to grow more branch filament that way. But if we max the surface tension just right, there's nowhere for it to go and the drops will stay. And then when we feed this a cheap precursor, silicon tetrachloride, this is what we get. These are single crystals by transmission electron microscopy of silicon growing along the 1-1 growth direction. They're 100% vertically oriented. Our initial scale up was, this is 1 centimeter. We've now scaled this up in barrel reactors on 6-inch wafers. We've grown square meters in our lab just within the last month by this fashion. At atmospheric pressure, with no vacuum conditions, in what literally is like one of the commercial toaster ovens that you pass the substrate through, leave it there for a little bit, and out the other side comes such a system. We then test this with an inert liquid, and we showed that indeed our physics predictions were right. This is really crappy silicon. Its diffusion length is only a micron because it's impure. It's saturated with gold or copper. You would never use this in a photovoltaic cell device because the first 1 micron would be live and the other 199 microns would be dead. But in fact, in this case, they absorb all the light with 200 microns, but everything is within a micron of being collected. And so when we infiltrate this with a liquid, we can collect all those carriers in material that's much cheaper and much less pure than you would ever tolerate in a standard planar photovoltaic system. Here's an example of a wafer grown from copper. Most people shudder when they think about copper and silicon because copper, it turns out, diffuses everywhere, which is why you never use it to make integrated circuit devices without extensive precautions and barrier layers. We actually love it because it's the ideal dopant in the sense that because it diffuses so quickly, it goes everywhere, which means it gets removed everywhere. And so we can oxidize the wires and then gather the copper out and then etch them off and there's no copper left. So we can use it as a cheap growth catalyst without degrading the minority carrier lifetime and actually recycle the copper in this way in a very cheap, fast process. Well, if we just grew these wires on a silicon substrate, you would argue you still had to pay for the cost of that silicon substrate, and it doesn't look anything like that device I told you we were shooting for. So I like to bet my graduate students only when I think I'm going to win. This bet was $1.98 at Petco. Why $1.98 at Petco? Because I don't like to bet more than $2. And you can buy Petco fish tank goop for $1.98. It's that clear stuff, RTV, that has the really important property. Its chemical formula is polydimethylsiloxane. But the important property is that its viscosity changes when you change the rate at which you peel it. If you peel it very quickly, it's very stiff. If you peel it very slowly, it's very flexible, just like peeling hair with a Band-Aid. And what we do, I won the bet, is we take that stuff, that tube of toothpaste, and we squirt it into our rods, and then we give it a rip, and off they come. Furthermore, any pattern that we impose here, if you took a laser pointer like the one I'm shining here onto this peeled material, will retain the diffraction pattern to 4 orders of spacing. So it's a beautiful freshman chemistry demonstration of how to impose diffraction order onto these new kinds of metamaterials of periodic arrays of stiff, light-absorbing, inorganic solids in the presence of organic, flexible, processable materials. Now, we've done this with polydimethylsiloxane. We've done it with Nafion that conducts protons and is used in fuel cell membranes. We've done it with hydroxide equivalents. We've done it with polymers that are already used in the photovoltaic industry that last for 30 years in the sun. And in all cases, this combines the ability to do high-temperature growth of semiconductors with the flexibility and processability of organic materials. I think this is arguably the best kind of organic photovoltaic cell because it's an organic photovoltaic cell when the organic material absorbs none of the light. So we take this material and we can also shrink that polymer. We do that by when we grow it with that tube, we actually add a high vapor pressure siloxane monomer, and so it just boils off. And by changing the ratio of the polymer to the monomer, we can either fully embed the rods, or we can partially embed them like this. And so now this does start to look like one of those pieces that I showed you, like the bottom half of that bologna sandwich, where we have our rods embedded in a proton permeable support that will allow us to make water into hydrogen from sunlight. Now you can also argue that if we only go this far, we still have an issue in that we still have that wafer to support that epitaxial growth in our process. Here's an example of one of these articles of manufacture, by the way. This is these microfiber silicon and a piece of rolled up plastic. It rolls, it unrolls. You can hold them in your hand, you can bend them. They look kind of like this. They look like jellyfish when you make them on a 6-inch wafer out of PEMS. But the next critical step is that what do we do in the process? We grow from cheap chlorosilane, it's a waste product in China, and we take our silicon fibers and impregnate them with our polymer and then give it a rip, like Band-Aid cutting off your skin with the hair, and we're left with these little stubs. And these little stubs of silicon are easily etched in a quick 30-second dunk in 1 molar potassium hydroxide. And that leaves behind the same holes that we started with, that then we electrodeposit more copper metal, that then we grow, and then we peel, and then we etch, and grow, and peel. And so this is a template, just like printing money with a template, that we use over and over again. And so we've shown that we can recycle that substrate, and by the time you've cycled it 10 times, its cost is negligible, and we've done it, we can project at least 100 times. Another important point is not only is this really cheap silicon, but there's no waste. There's no kerf losses. When you grow a crystal of silicon to make a big boule, the first thing you do is have to saw it up, and the thickness of the saw blades is such that you lose half of that precious silicon in the first place that can't be recycled. We have no kerf losses because everything that we grow is peeled and fully embedded into our material, and then we grow again and peel again. We use 1% of the silicon that you would use in a standard wafer to get the same absorption with the same potential efficiency from really cheap precursors with no processing and flexibility that you can roll the stuff up and unroll it to deploy it. Well, let's look at the optical properties. When we first did this, we knew that we would have one optical problem. At the appropriate pitch, at 2 micron diameter rods whose diameter is matched to the 1 micron diffusion length so we can collect all the carrier sideways, on a 7 micron pitch, which happens to be where we have the minimum reflection, because on this scale length, when the rods get too close, then they look like a bulk material, and they reflect like silicon would reflect with a high index of refraction. When they're too sparse, then light just goes right through it. That even then, when you look top down, that only fills 4% of the incident optical plane. So, according to the laws of optics, we should only get 4% total efficiency at best of light absorption because 96% of the light should go right through. Well, actually, we get fortunate by design because the spacing is on the dimensions of the diameter of light. So, ray tracing optics doesn't work here, nor does Brueggemann effective dielectric medium theory. In fact, because these are high index of refraction rods, any photons that are scattered are multiply internally reflected and are optically trapped in those rods as optical concentrators. And so actually at normal incidence, even in this array, we get 25% light absorption, and you saw that that material looked black, and the reason it looks black is that off normal incidence, then you have a lot of internal scattering and long path lengths, and you get essentially 100% light absorption. The way we get around that 25% limitation for that one time of day, that one day of the year when the sun is overhead, is you just scrunch up your fiber a little bit, and then you make something more like blades of grass on your lawn instead of aspen trees, and there's no time of day, no day of the year when the sun is at normal incidence over a material that looks like this in its morphology, as opposed to that perfect plane. So if you don't like scrunching up your material, the other way to do it is you can take those rods and introduce scatterers. Another $1.98 bet, because instead of clear plastic at Petco, you can get the white stuff. And what the white stuff has is it has the same PDMS, but impregnated in it as a binder is TiO2 or silica, cheap particles. And they use them to have its mechanical properties. We want their optical properties. Because then if a photon goes down the middle and hits a cheap scatterer, it gets bounced sideways, and once it gets bounced sideways, it gets absorbed by a rod and then multiply internally reflected and trapped in those optical concentrators, never to escape. And in fact, by using cheap scatterers and controlling where we put them, we can get the absorption properties integrated over time of day better in these systems than the best commercial anti-reflection coated silicon crystal and solar cell with no anti-reflection coating whatsoever, by just using simple photon management principles of cheap scatterers filling the volume in between the rods. Furthermore, because we can adjust the thickness of that polymer, we can put those scatterers anywhere we want to, and we generally put them in the bottom half of the rods to get both scattering forward and the backward direction to optimize our light management. Well, then we have to make a junction. The way we do that here is we thin that polymer, and we use it as an etch stop. After fully oxidizing those rods, we then cast that PDMS to thickness like this. We etch the rest of those rods that are oxide coated to reveal them except at the base, and then we make a diffusion just with spin-on glass to make a radial electrical junction. It's an N-type radial sleeve on top of these P-type dope-based systems. These are micro-photovoltaic rods, but not individual, made over massive areas, highly in parallel. And in doing so, and then filling them with scatterers, we can then make a top electrical contact and make cheap, flexible solar cells this way at 1% of the silicon you would normally use. But then if we expose the rods, we can get to our goal of making them useful for hydrogen production. We've done that. Our first shot was only sufficient in light scattering to absorb 50% of the light. The best organic solar cell out of 2 decades of research has now crept up to a little bit over 7% efficiency. Our first shot, only absorbing half of the light, we had 7.2% net solar conversion efficiency on a flexible, processable, cheap silicon precursor scalable over large areas. And furthermore, we've made systems that absorb 90% of the light and shown that in those systems things linearly scale. And so we believe that there's a clear path to getting the efficiencies in photovoltaic systems that approach that of single crystal silicon, but in a thin film, flexible, processable, massively deployed format. Well, we can also take catalysts, because unfortunately the sun isn't a laser, as my graduate students are disappointed to learn, and doesn't make correlated photons making correlated electron hole pairs. And so if we're going to make chemical bonds, you need 2 electrons at least to make a chemical bond in the same place at the same time. And so we need catalysts to take those uncorrelated single electrons from those uncorrelated photons and use them to make and break chemical bonds. In our first demonstration, we used and sprinkled platinum as the catalyst for hydrogen evolution. And we just did this as a demonstration system. We don't want platinum because no matter what we do, we'll never have enough abundant platinum to make a scalable system. My joke, by the way, is, as long as we have enough platinum in fuel cells to power school buses that cost $500,000, which is what they do today, we'll have a vigorous hydrogen economy consisting of stolen school buses, right? So we've got to find a way to replace that platinum, otherwise it's just a stunt. On the other hand, we can use it for demonstration purposes here because we want to show that not only can we collect carriers sideways, we can make chemical fuel with them and circumvent another issue. If we have a planar structure, it's well known that by the time you plate enough electrocatalyst on them to match the solar photon flux, you realize a thin metallic continuous film that reflects a lot of the light and then blocks the light to be absorbed underneath by the semiconductor. But we don't have that problem because we just need to sprinkle enough catalyst sideways that a catalyst particle is always within a minority carrier collection length of one of our absorbed photons. And also it turns out, because we have a lot of scattering, the photon absorption profile is not exponential like it would be with depth in a planar material. In fact, it's almost perfectly linear throughout the material because of this interesting optical property that we have in these metamaterials. When we sprinkle this with platinum and put it in contact with water, we get 0.5 volt of open circuit voltage. We get energy conversion efficiencies directly from sun to hydrogen of 7%. All of these are by far world records. And they really are this bottom piece. Now we haven't yet demonstrated the top piece because there is no known yet metal oxide that has the right band gap that is stable in water. And that's why we get paid to still do research, to assemble this top piece together with the rest of the system. We have shown, just in the past 6 months, that we are able to do a further step toward this development by actually combining a bottom piece with a top piece into a full article of manufacture that is such a system. Now to do that, because we don't have the material to make the top piece that will, without a voltage assisted, fulfill the entire sustainable requirements of oxidizing water, we're going to demonstrate that we can take the same piece on the bottom and the top and glue them together and at least make a system that would work. And what we do there is we grow a set of bottom rods, peel them off, grow a set of rods that will be on the top, peel them off, and then intervene with a conducting polymer that also passes protons, that also makes ohmic electrical contact between the top rods and the bottom rods. Just to show that we could do this, because if you were in the photovoltaic industry, and if you had to grow epitaxially a layer on the top of something and a layer on the bottom of something, you would have to use metal, organic, vapor phase epitaxy or molecular beam epitaxy to lattice match every atom on the second layer with the layers on the top. And that would be very expensive. And we transfer that problem into a soft materials problem. We do it by growing one material and then doing another, peeling them off, and then laminating them like making a driver's license. To demonstrate this structure, which is PowerPoint, we made all these ingredients. We made a peeled bottom layer, made a peeled top layer, made an intervening layer that made ohmic contacts. Here's that structure. You can hold it in your hand. It looks now like the PowerPoint that we had 4 years ago. Here are the rods down below. They're platinized. They make hydrogen from water. Here are the rods up above. They're intervening conducting polymer layer. This is an Nafion membrane, so it separates the gases, hydrogen and oxygen, with minimal crossover, which we've measured. We've measured the electrical contact between individual wires on the top and individual wires on the bottom. We know we can make suitable electrical contact between them with low resistance. So we know we can build these systems like this with two missing pieces. One is that we would rather use earth-abundant catalysts. This is the so-called volcano curve. It shows you the hydrogen evolution catalyst activity for various metals on a log scale. And of course, platinum is the best. And of course, nature's not kind to us, because platinum being the best is also one of the most unabundant elements on Earth. On the other hand, unlike a fuel cell that runs at an amp per centimeter squared, the solar photon flux is 100-fold less. It only produces 10 millionths per centimeter squared. On top of that, if we depart from the planar structure, and another design principle of these micro rods is they have a high internal area. So the same photon flux is now distributed its charge carrier flux over a much higher internal area. And that means the catalytic requirements are much less, because they have to pass many less electrons per unit area than they would if they were all funneled back to the plane. Because our internal area ratio to surface area is another factor of about 100, that 2 factors of 100 opens up our ability to use cheap catalysts like nickel and cobalt and molybdenum disulfide and still be kinetically competent where otherwise only the expensive metals would survive. And we've just shown this in a paper that we've just submitted, showing that we can in fact replace platinum with earth-abundant materials in this deeply integrated structure and maintain the same functionality with earth-abundant catalysts that are kinetically competent to match the solar photon flux, but only in these high aspect ratio structures. If you want to understand how important this would be, this is what on a log scale, the quote, catalytic breakthrough that comes out from our East Coast institution partners, cobalt oxide, and it's much lower in activity than other known systems, ruthenium oxide and iridium oxide. And the only way we can see to really use this is in this deeply integrated structure. Let me wind up with just one slide about what the DOE's Energy Innovation Hub is going to do. We're bringing together 200 scientists, 2 sites. One is at Caltech and the other is on the campus of Lawrence Berkeley Laboratory. We're not just chemists, we are physicists, we are material scientists, we are mechanical engineers, chemical engineers, product designers, trying to bridge 7 orders of magnitude in scale length all at once. Because we are not going to wait until we develop these systems to understand how to put them together, to understand how to scale them up, to understand how to build devices, to understand how to plumb them, because the world just doesn't have that much time left between here and where we have to get in 2050 to do it. So we're doing them all at once. We have product designers building systems while we're building improved pieces to plug into those systems. We know that those systems will be scalable when we make them and won't work when we make them the first time or the second time or the 5th time. The only way to get to the 6th product that works is to have the courage to build the first 5 that you know will not work and to learn from your mistakes. And to stimulate the scientific community to solve problems that are problems and not solve ones that are not problems. So our goal is within 2 years to have the first real prototype solar fuels generators with no lugs and no wires the size of this laptop, fully plumbed, fully demonstrated, that we know won't meet all 3 of those criteria at once. But we're going to be able to come back and show you the next year, and the next year we made it 30% cheaper, we made it 50% better, we made it 100% more efficient because of the work that the scientific community did to meet the challenge that we finally built one of these things and then set forth the metrics by which they can be improved. If you want to learn more about that, that's our Joint Center for Artificial Photosynthesis, JCAP. We love to get people involved because we need to use the best catalysts from wherever they are. We need to use the best light absorbers, and we need to enable that discovery to be our engine of innovation if we try to bring this from lab investigations into the reality that I think we really could use in an energy system. So with that, I hope I've given you some flavor for what I think about every day. Thanks so much, Paul, for the invitation.
Others will have questions. Yeah, Monica.
Hi, Monica from Rutgers. I'm part of the Cheesecake Hub for building efficiency.
Good.
And I'm just wondering if your materials could be possibly used for building envelopes, make buildings,
Right.
light catchers.
Yeah, so the photovoltaic, the solar electricity part of our flexible processing material is not yet. It was supposed to be publicly announced imminently is going to attempt, like many other solar technologies, to be commercialized. So we've licensed that out to major venture and corporate players because they think there's a real building integrated opportunity for flexible rollout solar things that could be integrated into windows and new rooftop materials and things like that. So it could play in that, but we're not ready yet to make, square miles of it. That's not what a university lab does. That's what the next phase of that scale-up would be. So that will come on sometime, we hope, sooner rather than later. That being said, people then often ask me, okay, well, how much is this going to cost, and are you going to compete with the industry leaders in photovoltaics? And the answer to that has to be, some people believe is yes, or they wouldn't be investing a lot of money into it. But my answer is, in an industry like that, a factor of 2 makes the difference between being a billionaire and going belly up. Right? And if I told you at this point that I knew the cost at scale to within a factor of 2, I would be lying. So I can't predict that swing as to whether or not it would end up being the world's greatest photovoltaic manufactured material at scale, or just another of the 1,000 solar companies that all think they have that and mostly don't. I can say that nobody has a way to make fuel directly, and so if you can get into a new function where there's no existing competition other than plants that have both arms tied behind their back on an efficiency basis, that then we start thinking about integrated storage with building efficiency and how to deal with the thermal management and load management issues at night, and then we start cost as less of an issue because there's no other choice other than doing something like this. So that's where ultimately you really want to go if you're a technologist when you don't have any competition.
Yes.
You talked a lot about the purity of the silicon and how important that is, but what about the purity of the water?
Right.
Nasty things like that.
Right. Great. So that's also a really great question. Because, you'll see demonstrations of people saying it works on seawater, but they're working on the anode. The anode is not a problem because that oxidatively cleans itself. And it's always impurity trace metal deposition on the cathode that poisons the cathode that's the real issue in all electrolysis systems. So we anticipate having to use reasonably pure water in order to avoid cathode deposition poisoning. I'm careful because I don't know what that really means until we build the system to know how pure is pure enough and what metals are or are not acceptable. We don't know the answer to that technically until we build one of these things and operate them. Rainwater might well be sufficient. That would be our best hope. Otherwise, we'd have to purify water through 18 megohm filters or something like that. And we yet don't know the cost of that either. We don't use a whole lot of water because it's not like thermal cooling for water. In fact, if you calculate the energy density in something like hydrogen you get from the water, you know, it's a small amount of water per day, but you would have to purify it to some level, and the question is whether or not rainwater is sufficient or not. We don't know the answer to that technically yet. So I hedged because I just don't have any data to tell you yes or no.
Last question.
Okay, how durable is this material for use outside? I mean, because you have a lot of these like very small silicon structures.
Yeah.
It seems like you have complexity like inside a microchip, which is fine inside the
Yeah.
closed environment of a chip package, but outside.
Right. Good. There's actually two questions here, which I'll kind of answer. The second one that normally gets asked, but it didn't get asked yet, so I'll answer the first one first. In fact, you don't want them perfectly regular anyway. We grow them that way to get control. You don't want them like aspen trees, you want them like blades of grass, right? Because then there's no angle of incidence time of day when you don't absorb all the sunlight. So if they were mished up a little bit, if something smushed them, that's perfectly fine, especially when a liquid's impregnating them and you don't have to make individual electrical contacts to every one like you need in a photovoltaic cell. That doesn't mean that we don't have to worry about protection from something like a hailstorm, and we'll have to figure out, you know, how you could actually implement it in a product that, you know, we are by far away from a product, right? I'm not going to tell you that we're there yet. We know about that. That's what companies have to do. That's not what we have to do now. Let me answer the second question that you didn't ask, and then we'll be done. People often ask me, well, you made hydrogen. We're going to make hydrogen first, because hydrogen is easier, 2 electrons from water, than reducing CO2 directly, which is 6 electrons from carbon dioxide to make some fuel. But in the end, it really doesn't matter. It just matters that you make a fuel. Because if we make hydrogen, we already have the technology to convert at world-class scale that hydrogen with nitrogen into ammonia. And it's done. You can use ammonia. We already know how to take hydrogen and CO2 and from reverse water gas shift and Fischer-Tropsch and make clean diesel. You want a liquid fuel? Give you a liquid fuel. We hardly lose any energy in those processes. What's important isn't to focus on the end fuel as opposed to the clean fuel feedstock, because we know how to make one into the other, so we're not hung up whatsoever. We would declare victory if we made clean, cheap hydrogen, because we could convert that to a liquid fuel in essentially a carbon-neutral way, and then use that to meet the transportation demand that we have the void to fill.
Thank you very much.